All right, 102 students, I've got a problem, kind of an older problem, but I thought I would work through it here. See if I can help out the question here. But it's from chapter 5. It's problem number 10. So this is the chapter on gravity. And it says here, how does the Earth's gravitational force on you differ when you're standing on the Earth than when you are riding in the space shuttle that is 400 kilometers above the Earth's surface? And the Earth's radius is 6,400 kilometers. So kind of drawing a picture in what would be going on is maybe I'll do a little stick figure on the Earth. And as they said, the Earth here has a radius of 6,400 kilometers. And that's the first part of it, because it says, how does the gravitational force on you differ when you're standing on the Earth? So this picture is for me standing on the Earth. Now, the other option, let me draw the Earth, and again with a diameter of 6,400 kilometers. And then put the space shuttle, what does it say, altitude here, when you're riding on the space shuttle, which is 400 kilometers above the Earth's surface. So maybe I'll just say the interaction between this is force number 1, and the interaction of you and the Earth here is force number 2. And since the universal law of gravity is given by this equation, that is the product of the masses and inversely proportional to the square of the distance between them, we could at least see from this that the force of gravity should be less as you get further away. And so the F2 should be less than the F1. So maybe I'll write it as F2 should be less than F1. Give me some kind of indication here of which one is bigger. So maybe I'll do it as a percentage. I think that's the best way to do it. I see that that's how the author did the solution here. So I will say, how much is your force in the space shuttle compared to on the surface of the Earth? So, we might be asking like something to the effect of, do you weigh 90% or 80% or 70%? But some kind of fraction here, okay? So this is how I'll solve the problem and coming up with some kind of fraction. Say, in the space shuttle I weigh 90% or something. So to calculate the force of gravity from the space shuttle using the universal law of gravity, I would go G, and M1 and M2 would be the two objects. So it would be the Earth and me, okay, divided by the distance between them squared. All right, now the distance between them squared would be these two added together. So it would be the 6,800. And here I have an interesting question I should ask myself. That would be the distance in kilometers. Do I want it in kilometers or do I want it in meters? And I know that if I use the value of G, which is the 6.67 times 10 to the negative 11, and that's in newtons meters squared over kilograms squared, I would want my distance in meters. However, I might not actually use the value of G because it's going to show up down here and cancel off. But just to err on the side of caution, I'm going to put in the distance in meters. So this 6,800 kilometers now becomes 6,800,000 meters, just in case I want to use the value of G. Now, if it cancels off, then I'm free to use whatever units, as long as I also compare them with units in the bottom. So I could have left that in kilometers, I think. But error on the side of caution, I'm going to put it in meters. Okay, now force number 1 is over here, so this would be on the surface, and so this would be G, this would be mass of the Earth and mass of me divided by the distance between them, and same thing up there, it would be the 6,400 kilometers, but I'm going to put it in meters and square it, just again to err on the side of caution. But now that I've written them both, I can be seeing how the capital G on top and bottom is going to cancel off. And even then, the mass of the Earth, and even then, the mass of me. So whatever percentage I get here, it's not going to depend on the object. So if it comes out to be 90%, I could say I would weigh 90%, but so would everything else. And so would that box over there, or so would the space shuttle itself. All right, well, luckily those canceled off, and then that tells me I didn't need to convert it into meters, but I'm kind of glad I did. Now we can flip and multiply. So this right here would be the 6,800,000 squared on the bottom, and this flipped on top would be the 6,400,000 and square it on the top. And now I'm going to get some percentage. And so let me grab my calculator here and go 6,400,000 and square it and divide it by 6,800,000. Uh-oh. 1, 2, 3. I think I went one too many, right? Yeah. And square it. Double check, okay, and then hit enter. And it looks like about 88.6%. So 88.6%. So there's my answer. I would weigh 88.6%, well, roughly 90%. I was just making that number up, but it was close to that. So 88, I'll call it 89%. And everything else, for that matter, would be 89%, as we can see. In fact, it would be true for, whatever the mass of the Earth is, because all these things, the mass of the Earth, the mass of the object, and the universal constant canceled off here. All right. Hope that helped.